All right, up on the table today we've got a Milwaukee M12 work light that's in for repair. You can see the M12 stick light version 0.72 on the PCB there. Had a friend give me this to look at and see if I can repair it, so we're going to try it today. See if we can find anything obviously wrong with it. I'm going to go ahead and power this up with 12 volts. Press the button. And nothing happens. And when I say nothing, I mean it draws no current and there's nothing at all happening with the light. I would expect these 4 LEDs along the side here, those look to be the battery indicator LEDs, and then there's 3 white LEDs in the little reflector here. In the back of this there's I don't know if I call it a heat sink, but a thermal mass that all of this is attached to. So, it doesn't work. Our goal is to figure out why. Alright, I brought the camera up a little bit just to make this easier. Now, I would definitely expect this to draw at least some current when you press that power button. If not, draw some current all the time. So, we're going to fire up our multimeter here. We're going to do some basic checks. We'll unhook this. So I'm in resistance mode. Let's go ahead and go into continuity here. So first thing I notice on this PCB is this black heat shrink thing, and it does kind of have what looks like almost a scorch mark on it here on the side. Not real sure what's going on with that. That part is labeled F1, which presumably means that it's a fuse. So let's go ahead and see if there's a connection across that guy. There is 0.3 ohms, so that's connected just fine. We can check the master power switch here, so that must be the off position, and then that is the on position, 0.18 ohms when it's on, so power switch does seem to work. I'll go ahead and leave that in the on position. I do notice there is an extra tab on this battery, which is presumably for a thermocouple or thermistor, something of the sort, which this tool seems to not use at all, which probably makes sense because this would draw a quite low amount of current. Honestly, with these tools, it may just be the battery charger that looks at that temperature sense line. We'll go ahead and bring our power back on here, and we'll switch this over to voltage. Another thing I'm seeing here right by this fuse is what looks to be a small voltage regulator. It might not be what it actually is, but we're gonna go ahead and check that. So meter set to DC volts. Probe this. We can almost guarantee it's not powered up because there's no current draw right now. Yep, 0. You can also make sure there isn't like a broken wire in the plastic cap there, which would be kind of crazy if there was, but there's not. So 12 volts there. Should have 12 volts on the ends of the fuse, I presume. Yep, 12 volts. 12 volts there as well. I think I'm going to go ahead and pop this screw out and see if we can't start tracking some of the traces and seeing where things are going. Because what I want to see is where that 12 volts stops, because I'm almost wondering if there isn't like a low voltage cutout circuit or something like that that is disabling a MOSFET and not allowing power to flow into the rest of the circuit. So this guy looks to be a T10. Yep. Alright, let's pop that out of there and see what's on the other side of the circuit board. There you go. It's a threaded screw. It actually has a bit of, I'd call it thread lock. It almost seems more like heat sink paste though, because it's still quite liquidy. Oh yeah, I bet that is heat sink paste that's on it, because look what's on the back there. You see there's some kind of a MOSFET. I'm guessing it's a MOSFET anyway on the back of there, and that screw was going through the hole in that, holding it in, so that stuff on the screw is definitely heat sink compound. So looking at the back of this, we can see the fuse is this terminal to this terminal, and then that goes into the switch, goes across the board here, and then back up to the top side. So in theory, turn the power supply back on. If we measure between ground and this point here, should be voltage. Doesn't look like there is. Is my switch still on? Sure looks like it. Zero. Alright. Maybe that's not where that actually is going. It's also coming out of that switch and going into quite a bit of other circuitry in this area too, so it's possible it's going to more than one place. I'd imagine all of this is live. Yep, sure is. Power to both sides of whatever this device is, probably some kind of a diode. 0 volts on the other side, maybe it's something else. Actually, this could be for the battery indicators, something, maybe not. Okay, I think I was wrong here. The via that should be connected to the positive rail of this board is this one, which is like almost covered by this little SOT23 package, and that looks to connect into this leg here. We turn this back on and measure the voltage here. We should have 12 volts, I think. Yep, there we go, 12 volts into, that's labeled Q9. One thing that is kind of sticking out like a sore thumb right now is that there's a solder joint on this device that does not look very good, and it magically turns on when you bridge that out. So that's interesting. Let's see if we can get a close-up shot on that. Alright, so you're going to have to bear with me here, getting real close to the circuit board. You see this component labeled D5 has this big ball of solder on the end of it, and then it's not really soldered to the pad that it's supposed to be soldered down to. And when I got in here and just kind of forced my probe in between that ball of solder on the component and the pad on the circuit board, the light flashed on for a second. So let's grab our soldering iron and just try to repair that solder joint and see what happens. Now, before I fully commit to soldering this thing, let's just try something quick. I'm going to set this to diode mode. I'm going to make sure that this diode is acting like a diode, because there's got to be some reason this thing is desoldered. Could be a quality control issue. It could also be that it's gotten really hot and it's melted itself off the board. Okay, it definitely still acts like a diode if I can make connections with it. There you go, 0.52 volts, and you saw when I had the probes the other way around, it said overload like this, which means that the device on there is only letting current flow in one direction, which is good for us. Alright, we'll get the old Heiko fired up. We'll bring in our fume extractor. Alright, soldering iron seems to be warmed up. Should be a pretty quick, easy thing to do. I've got I believe it's a 1.8 millimeter tip on the soldering iron. And this is 0.5 millimeter solder, which is great for doing this fine work like this. We should just have to come in here very carefully, touch the iron onto that component and add just a touch of solder. Alright, there we go. I think that is successfully soldered. Okay, so having a look at that same part again, you can see a lot of flux residue is what you can see Not sure if that actually successfully connected or not. Seemed like it did at the time, but let's go ahead and give it power again and see if it magically works now. It is quite difficult to get into the area where that device is without melting solder on other components. But let's go ahead and give this the old smoke test, and look at that. It is on and blinding the camera now. It's drawing 350 milliamps approximately. I did see one of these LEDs flash as if it were trying to indicate that I was low on battery. I also probably shouldn't run this for too long with that MOSFET off of its heatsink here. Let's go ahead and put the screw back in that quick. It's interesting to me that it was indicating a low battery because I'm running this off of a power supply at 12 volts. There could be some voltage drop in my horrible little alligator clip cables, but yeah, 12 volts should actually be 50, probably more like 70% of a charge on like an M12 battery. So, not sure what the deal with that is, but power it up. Yeah, you see the flashing LED there. We can turn our voltage set point up to 12.6, which would be a full M12 battery. Let's see what happens. Yep, there we go. We get all 4 red indicator LEDs when we first turn it on there. Yeah, there you can see that. So, interesting that it thinks that a low battery is at 12.0. I would expect low battery to be like 10.5 or something. And it does indeed continue to work at 10.5 volts. Okay, now we're down at 9.9 volts and this started to flash again. You can see there. And it cuts out at 9.6, which actually does make a lot of sense. That would be 3.2 volts per battery, or per cell, I should say. I don't know if it'll automatically kick back in, probably not. I have to turn it off and back on again. Also, I'm noticing that the current consumption is pretty consistent throughout the range of voltage that the battery would be at. Right around 354 to 356 milliamps, so let's call it 355, which means that it does actually consume a little bit less power as the battery voltage goes down. I believe the brightness is fairly consistent, and what's happening here is the reason this MOSFET has to be on such a big heat sink, and it is getting a little warm, I can feel it in the aluminum here. The reason this has to be on such a big heat sink is that they're using this as a constant current driver, so they're pretty much using that MOSFET or whatever type of transistor it is as a variable resistor to keep the current through the LEDs constant. And if you're curious, that's it's working out to about 4.5 watts on the input, which it does give off a decent amount of light. You can see the shadows it's casting there. And that's even with 2 fairly bright studio lights off to both sides here. Just out of curiosity here. Yeah, that part that I soldered back on is not getting warm at all. In fact, really nothing on this board's getting warm whatsoever besides the part that's attached to the heatsink down here. I can feel that starting to come through. Alright, so I did a little experiment with this now that it's been running for a while. First off, nothing's getting warm on this circuit board at all. Well, I mean the whole thing's a little bit warm, but nothing's getting super hot, particularly that diode that we resoldered on. That tells me that this was just a quality error from the factory. Soldering just wasn't good. It was touching just enough to make a connection for a while, and it died. Possibly through some vibration. I did notice that the standoffs on this thing for the reflector are like cracked, the top 2 anyway. I don't know if that's from the process of taking this apart or if that was because this thing was dropped or something like that, but I really wouldn't expect a solder joint to fail from vibration, especially on something that small. Like that's a tiny little 0603, now maybe 0805 component. That shouldn't fail from vibration. I did conduct a little experiment on this guy out of curiosity. I measured the voltage between here and here So that measured 8.4 volts across the entire LED string. 8.4 volts at approximately 350 milliamps that we're pumping into the input of the tool over here means that we have just a bit under 3 watts going into the LED array, which does make sense when you consider that there's 3 LEDs. They're probably 1 watt a piece. So that rating does make sense. It's probably going to last a really long time on an M12 battery, but one thing I will say, we're putting 3 watts into the LEDs. We're putting about 4.25 watts into the tool, so we're only about 70, maybe 75%, if you're lucky, efficient. And that's because we're using whatever this device is to regulate current. This could be a transistor and some current regulation circuitry to get it to output the same current all the time, or it might be something as simple as an LM317 voltage regulator, which can also be used as current regulators. It's kind of disappointing. I kind of would have expected this to have like a buck converter in it and a constant current source out of that, because that would have made it probably around 90% efficient, which would give you longer runtime on a battery operated tool like this. You might get 15 to 20% better runtime if it had something like that, which is a significant difference. This is pulling 350 milliamps. I think those M12 batteries are 2200 milliamp hours. Maybe they're only 1.5 amp hours. I actually don't know what the default ones are. Maybe they're 3 amp hours. If it was 3 amp hours, it'd last about 10 hours, and if you get 20% more than 10 hours, it's 12 hours, and that's a decent runtime difference. So this is kind of a controversial opinion, but this is why I don't buy like Milwaukee and DeWalt power tools, because they're super expensive and you're just not really getting anything special for your money. Like, this is a 3 watt LED array. It's got quality control issues, and yeah, what am I paying $50 for with this thing? I will say right now it is on sale for $35, but it probably does go on sale for $35 often, but $50 for this, and that's not even with a battery, that's bare tool. I just don't see how this thing is worth $50. Like, their margins have to be insane on this kind of stuff. I don't know, maybe I'm just bitter because we found what was an obvious quality control error on something that's a decent chunk of money. But I've certainly spent a lot of money on flashlights before. I've got a couple of through-night flashlights that are worth $50, and those are quite a bit brighter than this is, and they don't require a proprietary battery. So on the bright side, that was a really easy thing to fix, so I can give this back to my friend and he'll be happy about it. And yeah, if you're having problems with your M12 work light, pop it open and check the solder joints, I guess, because apparently the quality control on these boards is not very good. Anyhow, I'll see you in the next one, guys. Bye.